Welcome to our video tutorials for our PC tool openSYDE. In this video, we would like to introduce you to the topic Hardware Configurator. If you are not yet familiar with the basics of openSYDE, we recommend the video Basic Introduction to openSYDE and the videos on using the data pools from this series. The programming of a controller from STW is done via the functions of the BIOS. For this purpose, STW supplies the so-called target support packages which contain the BIOS. Among other things, it contains all the functions for initializing the inputs and outputs of the controller, for setting an output, and to read a measurement result of an input. During application development, you will have to program a number of BIOS functions yourself for each individual input or output, which means you will have to take the BIOS functions from the user manual and program each individual parameter required in the code of your application. For controllers such as ESX3CS, where the Hardware Configurator feature is already available, openSYDE can conveniently support you with this programming. The openSYDE user interface displays all the inputs and outputs of the controller, and each required parameter can be configured with a mouse click and stored in a data pool. Code is then generated that you can integrate into your application. Your application must be based on the STW template. Then the so-called HAL driver uses this code to operate the inputs and outputs according to the settings you have made in openSYDE. For programming the logic of your application, you can now use data pools directly for measurement results of the inputs. Setting the outputs to a certain value is also done via the data pool and the HAL driver. But for safety reasons, the change of this data pool value is reserved for your programming in the application. We will take a closer look at the implementation of the Hardware Configurator feature using the associated example in the target support package of the ESX3CS. The TSP has already been installed on the PC in preparation for this video. It contains a completely elaborated example of the Hardware Configurator consisting of an openSYDE project and the corresponding programming project for the application in C with the IDE code blocks. We first start the openSYDE project of the example. We can already see on the start page that this example uses a limited number of inputs and outputs for demonstration. Analogous to the programming of these inputs and outputs, which we will look at in detail in a moment, you could also extend this application to make it usable for all inputs and outputs. In this example, the controller is only operated on the CAN1 interface. CAN2 is enabled but not used. The Ethernet interface is deactivated and is also not used. On the data block, we can already see the two data pools are assigned to the application. We find this confirmed under data pools. We see a data pool of the type diag and a data pool of the type HAL. The diag data pool HAL has been created in this example for demonstration purposes only, and it is not required in this form for the functionality of the Hardware Configurator feature. We will look at the purpose of this data pool in more detail later. If we look at the details, we see from the comment fields that variables are created here to store measurement results of the inputs, as well as various status information. For the outputs, it is, for example, voltage values that are set, and again also various status information. The diag data pool and its variables are only used for the inputs and outputs actually used in the example. HAL non-safe is a data pool automatically generated by openSYDE and is mandatory for the application of the Hardware Configurator feature. The HAL data pool is a special data pool. By double-clicking on this data pool, openSYDE jumps to the tab Hardware Configurator and offers an overview of all configurable channels on the ESX3CS. openSYDE can only offer the Hardware Configurator in this form if the hardware description file for the controller is available. This file is automatically created during the installation of the openSYDE TSP, even if you program your application based on the STW template application independently of this example. The hardware description file contains the description of all configurable inputs and outputs of the controller, as well as the configuration options for them. If the use case column says not used, the channel will not be processed by the Hardware Configurator function. We see that only the 6 inputs and outputs mentioned at the beginning are used in this example. What does use case mean for a channel? This can be easily demonstrated using the example of a multifunctional input such as the IDA35V. The input can be used as a measurement input for the digital state, the frequency, an incremental position decoder, or analog voltage. These options are called use cases. For each use case, further parameters can be specified in detail, which are required for initialization. If we compare this with the description of the BIOS in the user manual of the ESX3CS, we see that openSYDE offers the initialization parameters clearly and conveniently for setting. Here, openSYDE only offers the selection of available parameters that are really needed for the configuration of the input in the selected use case. The same applies to the outputs. Versatile outputs such as OP2A can be used as digital, PWM or current controlled outputs. In the case of current control, a corresponding number of parameters for frequency and current, as well as the control behavior, must be set. For simpler outputs such as OD2A, only the use cases PMW and digital can be selected, and no further parameters must be considered for the latter. However, we see with the outputs that no concrete values can be configured, for example, an output voltage or duty cycle. For safety reasons, this should not be done via generated code, but is reserved for concrete programming in the application. This minimizes the risk of accidentally setting high voltages or currents at an output. In the Hardware Configurator, based on the hardware description file, all input and output types of controller are displayed and offered for configuration with all parameters that can be programmed via BIOS functions. All settings that you make here are saved in the HAL data pool and made available directly in the programming project as code in C&H files for application programming using the Generate Files function. We summarize the necessary steps up to this point once again. We have installed the development environment, code blocks, and openSYDE. We have downloaded and installed the component display package for the ESX3CS from the cloud. We create an openSYDE project with an ESX3CS controller and import the associated data block via the openSYDE TSP. This creates a programming project for the IDE based on the STW template application. This also creates the C routines for the HAL driver. Using the openSYDE user interface, we configure the inputs and outputs with the Hardware Configurator. Through code generation, we save this configuration in the form of a HAL data pool in the programming project. If we start the HAL example in openSYDE directly, as demonstrated earlier in the video, these steps have already been carried out. We will now take a closer look at how we can continue to use the settings from the Hardware Configurator through further programming and what tasks the HAL driver takes over for us in the process. We first add the path to the IDE according to the installation of this PC so that we can start it from openSYDE and then change to the IDE code blocks to the C programming project of the example. The example is here relative to the openSYDE project, so we start the IDE. The project file for code blocks is in the PJT folder. The project contains the BIOS and openSYDE parts. Under openSYDE, we see directories for generated data and routines for the Hardware Configurator. You will also get these routines if you start programming your own application with a template instead of the example project. During the demonstration, we will go into the code that was programmed for the example in addition to the template, and from now on, we will only stay in the example project. We open the main C program of the example project. It starts with the initialization of the system. This is followed by the initialization of the CAN interfaces and, if configured accordingly, the Ethernet interface. Then the openSYDE server is initialized and the task system is initialized and started. This is followed by the main loop, which is only terminated by switching off the ignition signal. In the main loop, there is an LED handler that makes the user LED on the controller change colors from green to orange. Compared to the template application, the following have been added. The initialization of the Hardware Configurator by the routine OSY HAL init, which is part of the HAL routines in the template, and the handling of the Hardware Configurator data by the routine mhandle HAL data within the main loop, which was developed specifically for this example. Let's start with the initialization of the Hardware Configurator. We give this initialization function the structure information of the HAL data pool and thus the information about which parameters can be set at all. The function then handles the initialization of the inputs, the supervisor and the outputs one after the other. Using the example of the function for the inputs, we see that it loads the concrete values set in openSYDE as a so-called dataset into the data pool that was empty until then. Then follows the concrete configuration of all inputs according to the settings in openSYDE by the function ESX3CX in init. Here, the use case is first determined for all inputs. In our example, it is, among other things, a measurement of the voltage with input IDA 35V1. We get to the function mVoltageInit. This function then calls the BIOS function xInInit of the ESX3CS with the data of the HAL data pool and initializes the input accordingly. In the same way, the configuration of all outputs works with the corresponding chain of function calls. We return to the OSY HAL TRG config init and trace the call for the configuration of the outputs. The dataset for the outputs is loaded into the data pool. Then follows the concrete configuration of all outputs according to the settings in openSYDE by the function ESX3CXOutInit. Here too, the use case is first determined for all outputs. In our example, it is, among other things, the setting of the voltage with the output OAV10V. We arrive at the function mVoltageInit. Since the HAL driver was written for the ESX3CS and the ESX3CM, the case distinction is first made according to the control type. This function then calls the BIOS function XOutInit of the ESX3CS with the data of the HAL data pool and initializes the output accordingly. The HAL driver therefore checks all inputs and outputs activated and parameterized via openSYDE and initializes them accordingly. Now the question is how we get the measurement results of the inputs and set the outputs to concrete values, for example a concrete voltage. We return to the program main C. Here the cyclic tasks for openSYDE server and hardware configurator have been initialized. In the task for the hardware configurator, the functions OSY HAL TRG handle inputs and OSY HAL TRG handle outputs are called. Let's start with the inputs. In the function ESX3CX in update values, we see that again, depending on the use case for all inputs, the corresponding function of the BIOS is used to fetch the measurement results. They are all stored in the HAL data pool. This works similarly for the outputs. In the function ESX3CX out update values, we see that depending on the use case, here again demonstrated by the example of setting a voltage, first the voltage value to be set is determined from the data pool. Then the output is set with the corresponding function of the BIOS. Everything shown so far is template functionality that you do not have to program yourself. We will now look further at the usage of these mechanisms in the example. To do this, we go back to the main loop. Here we find the addition to the template mhandle HAL data. In this routine, the diag data pool HAL and the HAL data pool HAL non-safe are first locked to ensure data consistency against concurrent data access. This is followed by the exemplary use of the data from the hardware configurator. In this example, the data from the HAL data pool generated by openSYDE is copied into the diag data pool. For example, the init status of input IDA35V1, i.e. channel 1 is copied into the variable S16 init status. We do the same with the runtime status of this IDA35V input. In the third program line for this input, another variable is used. However, we can see from the declaration that here too there is actually a value from the generated HAL data pool behind it. It is the variable P32 value which represents the measurement of this input. Depending on the use case applied to the input, the value of this variable has different meanings. In the case of IDA35V, this can be a voltage, a current, a frequency, etc. To avoid always having to work with P32 value, these defines are provided in the HAL driver to make the code easy to read. Back to the routine mhandle HAL data. We see that in the same way the status and measurement values of the voltage on channel 5, i.e. the IACV1 input and the digital state of channel 9, i.e. the IDA5V1 input, are written to the diag data pool. Thus, the three inputs are treated which we use in this example. For the outputs, we proceed in the same way as for the inputs in terms of status information. Setting a certain value for an output is also done via the HAL data pool, but for security reasons, it should not be done by generated code, but by a concrete specification on the part of the programmer through the application. We see that the variable S32 HAL out set.01 used here for the output OP2A1 again corresponds to the HAL data pool value. However, this time it is fed from the value of the diag data pool HALC. We will take a closer look at which concrete value this corresponds to in a moment. The same applies to the value of the digital state of the output OD2A and the voltage value of the output OAV10V. At the end of the routine mhandle HALG data, the data pools are unlocked again. Digital state, current and voltage of the outputs are thus set by the HAL driver to the values that are in the HAL data pool, and these are supplied with concrete values by the diag data pool in our example. To understand how these values are created in the diag data pool, we return to the openSYDE project of the example. A dashboard is defined under System Commissioning. For the outputs, we see three so-called writing widgets: an on-off switch for the digital output OD2A, a slider for the setless stepping of the set point for the current controlled output OP2A in the range 0 to 100,000 microamps, a controller for the stepless setting of the voltage for the output OAV10V in the range 0 to 10,000. Since these are millivolts, we can adjust the voltage between 0 and 10 volts with this controller. If we switch to edit mode, we can see where these settings go through the widgets. For the on-off switch, it is the data element ESX3CS HALG OD2A1 value. If we scroll through the data elements, we see even more clearly that it is the variable of the diag data pool HALG. The same applies to the controllers, which also supply the HALG data pool with their values. This closes the circle. Via the dashboard, we can make settings during an operation which are transferred to the data pool on the controller via the diagnostic data pool of openSYDE, and then cyclically converted into real configurations of the outputs by the HAL driver in the controller. We now want to test the example live on a controller. First, we take another look at the configuration in openSYDE. The controller is connected to the CAN bus. A dashboard is prepared for displaying the inputs IDA5V1, IACV1 and IDA35V1, as well as for configuring the outputs OD2A1, OP2A1 and OAV10V. Based on this, we design our experimental setup for the following demonstration. We use an ESX3CS from a starter kit and connect the controller to the breakout board using the cable provided. We connect the power supply to the breakout board and connect our PC with openSYDE to the CAN1 interface via a properly terminated cable. On the breakout board, we make connections between inputs and outputs with cable jumpers. We connect OD2A and IDA5V as well as OAV10V and IACV, and at the same time IDA35V. We do not use the output OP2A in the following demonstration. We additionally provide the output OD2A with an external low impedance load. Next, we configure the controller according to the specifications of the sample project in openSYDE. To do this, we run the device configuration in System Commissioning. Our example application would actually already be finished, but we go through the steps of its creation again. We generate the code and thereby obtain all the data pools for the hardware configurator and the diagnostics, i.e. the data for the dashboard. In the development environment, we use this to build the application. This was successful. The compiler concludes the process with the message that the application could be created without errors. We flash this application onto the controller with openSYDE. In the update mode, we recognize that the newer application is available. We update the controller. Then we exit the update mode and reset the controller. The sample application is now running. We go online with the dashboard and already see results for the voltage measurement. We switch on the output OD2A and see that the input IDA5V shows the state high by the green circle. If we switch it off again, the low state is displayed. And with the controller for the output OAV10V, we set values from 0 to 10 volts and measure this voltage with the two inputs IDA5V and IDA35V. We had noticed when looking through the application code that the hardware configurator always first determines the use case for the respective input or output, then initializes them accordingly, and then writes the measurement results into the data pool or sets the values for the outputs with the data pool values. We can prove this by reprogramming a measurement input using openSYDE. We leave the diagnostic mode and switch to the hardware configurator. The IDA35V input measures voltage in the current configuration. We can easily reconfigure this to digital measurement with openSYDE by selecting the appropriate use case. We generate the code again. And we build the application again with the new code, i.e. the new use case for the measurement input. We flash this new application onto the controller with openSYDE again. The process is complete and we exit the update mode, thereby starting the new application and going back to the dashboard. In the user manual, we can still look up which measured value we can now expect. So far, we have had the use case voltage, and therefore we could expect a value in millivolts between 0 and 35,000. We were able to observe this earlier in the dashboard as well. Now, if we work in the digital use case, the measurement result will be 0 for state low and 1 for state high. Here we see in the IDA35V description that voltages greater than 7 volts are interpreted as high and less than 6 volts as low. We go online with the dashboard. We change the output value of the voltage output, whose voltage we continue to measure with the input IAC-V1. IDA35V1 now measures the digital state and detects the low state, i.e. 0 at about 6 volts, and the high state, i.e. 1 from about 7 volts. These values are not millivolts, of course. We have not adjusted the widget in this respect. This demonstration makes clear that a reprogramming with the support of openSYDE is very easily possible without having to program the BIOS functions of the controller ourselves. We hope to have brought you a little closer to the hardware configurator of openSYDE. We summarize. We use openSYDE and the development environment to program the application. We program on the basis of the template from STW and can thus use the HAL driver. We make all settings for the configuration of the inputs and outputs comfortably via the graphical user interface of openSYDE. These settings are transferred from openSYDE to the development environment as code in the form of data pools. In the application, The HAL driver uses the data pool values to initialize the inputs and outputs. The measured values of the inputs are stored in the data pool. The values for the outputs are determined from the data pool and the outputs are set accordingly. The necessary programming with BIOS functions of the controller is already provided by the HAL driver. We can simply and directly use the data pools for the further application-specific logic. We put the completed application into operation on the controller. Modifications can easily be done via openSYDE. We simply repeat the steps for setting the inputs and outputs in openSYDE, generate the code, and rebuild the application. In the series of openSYDE videos, other videos appear on this channel that deal with the details of single features. I wish you every success in using openSYDE.